Okay, the word differentiability implies that the derivative exists. So what we're going to be talking about is how to tell if a function is differentiable at a point. So as long as the derivative, which is the slope, exists, we say that it is differentiable. Okay, now the important thing to remember is that if a function is differentiable, which means the slope exists, then it means that there has to be a point there. So differentiability really implies continuity, but just because a function is continuous does not necessarily mean that it is differentiable. So we'll look at both cases. Another thing to keep in mind is differentiability implies local linearity. What that means is if you look at a graph on a calculator and you zoom in super close, if a graph is differentiable, when you zoom in, it's going to straighten out to look like a tangent line. If you keep zooming in and it doesn't straighten out to be a line, then that's how you also can tell that it's not differentiable. So let's look at a couple different cases. So we want to try to come up with a function that is not continuous at a point and it is not differentiable. So this would be one example. So at this point right here, you have a hole, so it's not continuous, and so you don't have a point there, there's no slope, so it's also not differentiable. Another example would be a graph that has an asymptote. So a graph that looks maybe something like this. So at that asymptote, obviously it's not continuous, and if you don't have a point there, it can't be differentiable. Okay, so now let's look at a couple scenarios where the functions are continuous, but where the slope does not exist, so it's not differentiable. There are two scenarios that we talk about. One is when you have a sharp corner, or also sometimes it's called a cusp. So if you have a graph that looks like this, that's typically your absolute value graph. This is differentiable everywhere, right? I can graph this without lifting my pencil, but at the corner, it is not differentiable. There is no slope that exists there. So at the corner, we say it's not differentiable. Same thing for a graph like this. This is called actually a cusp. Same thing. It is continuous, but is not differentiable. The other type of graph where you would not have a differentiable point would be if you have a vertical tangent line. So if you looked at a graph like this, and I'm going to exaggerate it. So this is a continuous graph, but right here, there is a vertical tangent line. So if you think about a vertical line, the slope is undefined, so we would say it is not differentiable where you have a vertical tangent. Now, graphically, it's pretty easy to tell when it's differentiable, but what we want to be able to do is prove analytically why something is not differentiable. So let's look at one of our most basic graphs that has a corner, which is an absolute value graph. So let's look at the graph of an absolute value of x minus 2. So we have a vertex at 2, so the graph looks something like this. So this is continuous everywhere, right? Just from the graph, I know I can draw this without lifting my pencil, but it is not differentiable at x equals 2. And just from the graph, we know because it has a corner, we can say it's not differentiable, but let's prove this analytically. And what we're going to do is use the definition of the derivative that we learned previously. So we learned previously that this is one of your definitions of the derivative. There's two. Oops. Should be x minus c. So this is f prime of x, really. This is your limit definition of the derivative. So this is really your slope. So in order for it to be differentiable, this has to exist. Now, on this portion of the graph, this is just a straight line, so the slope of that graph would just be -1. The slope on the right side of the graph is +1. But what we're going to notice is that the slope does not exist at that point x equals 2. And what we're going to do is look at the left and the right hand limit. So if I look at this graph as I approach 2 from the left side, so when you're looking at this graph, and as you're approaching 2 from the left side, the slope of this graph is always -1, right? Just the slope of that line. I can do the same thing as I approach 2 from the right-hand side. So again, this just represents the slope or the derivative. As I approach 2 from the right-hand side, the slope of this graph is positive 1. So as you approach 2, you are not approaching the same value, so that's why it's not differentiable, and that's why graphically it creates this corner.